So here we are in the Eclipse IDE, and we're about to take a look at that example where we're going to make up a comparable rectangle from our original rectangle. Let's just very quickly and briefly review the history behind this. You recall we came up with a geometric object, and it looks like something like this. This is at least part of the code. And from there, we made ourselves a rectangle, and again, this is the code for the rectangle, or at least part of it. And now what we're going to do is extend our existing rectangle code to a new class called comparable rectangle. And the difference is that this comparable rectangle is going to implement the compare to interface. So the only new pieces here are the code for the comparable rectangle and a piece of code to actually test it. Let's look at the program that's going to test it first. It's called Sort Rectangles, and it's somewhat easier to look at. So let's look at it first because it's simpler. You can see that what I've done here is created an array of this new object comparable rectangle called rectangles, and I've set it equal to new comparable rectangle 3.4 5.1. That's going to effectively call the construction from the previous rectangle to simply make a rectangle of width and height 3.4 and 5.4. But this is going to be a comparable rectangle, which means now, unlike the original implementation, it does implement the compare to interface, and we'll take a look at how it does that in just a moment. I'm also creating an additional 3 rectangles in this process. So I've got a total of 4 news here with various different dimensions to a bunch of different rectangles. Now the basis upon which I'm going to plan on doing my comparison is on area. So the smallest rectangle will be the one that has the smallest area, and the largest rectangle will be the one with the largest area. It's kind of difficult to look at these dimensions and know just by looking which is going to come to the smallest amount of area and the biggest amount of area. So we're going to have to wait and see how that pans out. But no doubt I've not got them in any particular order here, so the order that they should print will be somewhat different than what you see them declared in this case. Because my comparable rectangle implements the comparable interface and therefore overrides the compare to method, it is compatible with Java util arrays.sort, which is going to allow me to use the sort method of this utility function in order to sort my rectangles. After I've sorted them, I'm going to do something similar to what you saw in the other examples where we were using the sort utility. I'm going to iterate through them based on the order that they exist in the new sorted array, and I'm going to print them out one at a time. I'm going to print out the rectangle, which is going to actually do the toString method, if you recall from way back, that we defined for our rectangle. And also it's going to print the area of the rectangle as part of doing that. So we should be able to confirm that the rectangles have indeed been ordered by area just by looking at that part of the output. So the next thing we're going to do is take a look at the code for our comparable rectangle. Well, we did say we were going to have comparable rectangle as a child of rectangle, so you can see that that's what we're doing in the very first line of code. Public class comparable rectangle extends rectangle, but it also implements the comparable interface using as the generic type comparable rectangle. So let's take a look at how we do this. Well, the first thing is we're going to create a constructor for comparable rectangle which takes 2 doubles, a width and a height. And we're going to actually call our superclass constructor passing those parameters onto it, and that's how we'll construct our rectangle. So far then, we've simply got a duplication of whatever was in our rectangle class. But now here's where things get interesting. We're now going to override the abstract compare to method in the comparable interface with a concrete implementation. And here's what it does. Well, first of all, let's look at the override part. Public int compare to comparable rectangle O. Our implementation says that we're going to get the areas from the current rectangle and the one that's been passed as an argument. In other words, from this rectangle and the rectangle that exists as a parameter here, O. And we're going to compare those two areas. So we're going to get the area of this rectangle and compare it to the area of rectangle O that we've been passed as an object or parameter. If the current rectangle has a bigger area than the parameter rectangle, we're going to return +1 to indicate that. If, on the other hand, our current rectangle has a smaller area than the object that we've been passed as a parameter, we're going to instead return -1. If both the if and the else part fail, then the only conclusion we can make is that the areas of the two rectangles must be equal. And in that case, we'll return 0 to indicate that they're both equal. So that's consistent with the numeric return types for the compare to method that we looked at earlier. +1 when it's greater, -1 when it's less than, and 0 when it's equal. Now, while we're at it, we're also going to override the toString method so that we can get the width reported, the height reported, and the area of the rectangle reported as well. This part, for our purposes here, is the most important part because we want to see if it really did sort by area. So we better output that as one of the things that gets printed so that we can tell whether or not they really did get sorted by area. Okay, so let's just tidy this up a little bit because it looks kind of ugly here. Okay, and I think we're now ready to go ahead and test our implementation. So let's go ahead and run this. And there's our output. Let's take a close look at it now. And before we do, let's go ahead and put the source code up for sort rectangles so we can take a look at the original order. So you can see that originally the first rectangle was the one that was 3.4 by 5.4. As it turns out, that is the one with the smallest area. It's got an area of 18.36, and that is still the first one then that appears. However, the next one that was originally 13.24 by 55.4, I guess it's pretty obvious that's going to have the largest area. And you can see it's moved to the last position here, having an area of 733.496. Our last rectangle was 1.4 by 25.4, and it wound up in second place right here with an area of 35.55 and a whole bunch of 9s after it. And finally, the 7.4 by 35.4 rectangle wound up in third position here. So let's take a look then. We've got 18.36, that is the smallest area. 35, roughly double, is next. And then 261, which is significantly larger, is next. And finally, the largest area of 733 is the last area. So indeed, we did change the order, and they are in sorted order now, whereas they did not begin in sorted order. So that worked out exactly the way we would hoped it should work out.